Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will perform matrix multiplication using Python and offer more details on executing Python production jobs on the Betzy Linux cluster. After logging into Betzy, we accessed the Login2 node. For our production jobs using Python, we'll be using the work folder. I've created a folder named Python on Betzy within the work directory. Inside the Python on Betzy folder, we have 3 files with the same name but different extensions. First, let's examine the file with the F90 extension. This file contains the Fortran subroutine we discussed in video 36. Next, we'll look at the Python file, which is highlighted in green, indicating that it is executable. We'll set the matrix dimension to 32,768 and use the NumPy routine. In video 33, we noted that the computation took approximately 39 seconds using the Fortran program for this matrix size. In video 34, using Fortran MKL, the computation was completed in about 31 seconds. Let's examine the job script file with the sh extension. This script is similar to those we've used before with Fortran and MKL, and it requests 128 cores on a single node. We'll load the matplotlib module, which also loads NumPy and the Fortran to Python command. We're setting OpenMP environment variables, and we know that the NumPy routine uses this. The Fortran module is constructed using the same Fortran to Python command demonstrated in video 36. However, we've substituted the Intel Broadwell architecture with the X-host option. Finally, we'll execute the Python program and use script commands to measure the build and execution time. The remainder of the job script is unchanged, and we make copies of the files used for this job. Before submitting the job to the Slurm management system, we clear the terminal. Once submitted, the job is assigned a job ID number. Using the slurm queue command with the me option shows that the job has been running for 20 seconds. Let's examine the slurm output file with the correct job ID number. The matrix multiplication completed in about 35 seconds, demonstrating successful parallel computing. This confirms that NumPy routines can utilize OpenMP for parallel processing. In video 33, the computation duration was approximately 39 seconds with the Fortran program for this matrix size. In video 34, the Fortran MKL routine completed the computation in about 31 seconds. This indicates that the NumPy routine achieves performance that falls between the Fortran program from video 33 and the Fortran MKL program from video 34. Let's list the files created in the folder. We notice new files, including copies of the original files used in this computation, with the job ID number appended to their file names. Before submitting the job once more to get a better measurement of the CPU efficiency, we'll make some changes to the job script with the Emacs editor. We'll skip the building process of the Fortran module and reuse the existing Fortran module. This approach will provide a clearer indication of CPU efficiency during parallel computing. Before submitting the job, we clear the terminal. After submission to the Slurm management system, the job is assigned a job ID number. After waiting for a while, we see the job has been active for 23 seconds. Once the job finishes, we examine the results in the output file using the correct job ID number. The matrix multiplication was completed in approximately 37 seconds, which is about 2 seconds slower than the last test. The CPU efficiency was about 68%. Memory usage was approximately 25 gigabytes, as expected for this matrix dimension. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder Cluster, Work, Support, Parallel, Computing, YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos, and you can copy any of these files to your home folder. In our next video, we will use a Python program that uses the Fortran MKL library on the Betzy Linux cluster. I am looking forward to the next video. Wishing you all happy computing in the meantime.